Hello everyone, my name is Bao Minh Tran, and today I have a presentation on reinforcement learning for automatic DBMS knob tuning. DBMS stands for Database Management System, which is an application that allows users to interact with a database. DBMS knobs are tunable parameters that database administrators can adjust to achieve better DBMS performance. They are categorized into two types: static knobs that needs the system to restart so to have some effects, or dynamic knobs on the other hand don't need the system to restart. We can think of the DBMS knobs like a control of the car, and we have the puffable side, which is like a car's full tank. The larger the tank is, the further we can go. However, it will slow down our speed. Or the thread concurrency is like a number of cylinders in our engine. More cylinders mean faster performance, but that could be inefficient in a crowded CPU or a crowded road. So these knobs are an integral part of data-intensive applications. So experts have been trying to improve them. The first efforts were made in the 1970s, which is called the self-adaptive system, but it was mainly about physical database design. And 2 decades later, the self-tuning systems were introduced. Depends vastly on its predecessor, but introduced a new mechanism for automatic adjustment of DBMS knobs. And before the 2010s, there were two core methodologies. The first one is heuristic algorithms, simulates a database environment and then provides the developers or user with questions to determine which knobs to be tuned. Another methodology is cost-based algorithm. They're collections of search techniques and algorithms like greedy search, branch and bound, genetic algorithms. But they do have some limitations. For example, heuristic methods, they rely on preset rules to suggest configurations but fail to adapt to the dynamically changing environment. Cost-based methods employ really efficient techniques, but they fail to apply to real-world use cases due to its extensive simulations. So this is when the machine learning came into practice. There's a subfield artificial intelligence that gives computer the ability to learn without explicitly program, and they're adaptable to diverse and ever-changing environments, handling dynamic workloads interdependent in parameters across different types of databases. So, for example, like auto-tune capitalize on supervised learning, Bayesian optimizations use a probabilistic approach, or deep learning techniques embed neural networks to handle the complex relationships between the knobs. So, my report mentions vastly about the reinforcement learning approaches, which is the branch of machine learning. But here we can see that the algorithm acts as an agent interacting with the environment by receiving rewards or penalties according to how its actions influence the environment. And there are some certain aspects of RL mentioned in my report, like actor critic, advantage actor critic, deep reinforcement learning, and deep deterministic policy gradient. Some of its strengths, like it can adapt to dynamically changing environment, it can work well with limited training samples, it can strategically explore new actions while refining already known strategies for optimal performance, it can handle high-dimensional environment, and it can enable collaborations between different agents. So, to clarify how these algorithms apply in the real world practices, I introduced the Bluetooth system, which was developed to automatically tune the database configurations for IBM DB2. You can see that a set of SQL queries then sent to the IBM DB2, but it won't be executed immediately. Instead, it will be fetched information to create a query execution plans, which then be vectorized to numeric vectors and sent to the agent. And the agent will then produce the knob configurations and run these query workloads on these new configurations, and then the environment will return the performance matrix for the agent to further strengthen its model. And having a deeper look in our agent, we can see that Bluetooth develops the actor critic model to a better one called advantage actor critic A2C. This improvement is mostly about a critic component. Basically, the original model fails to compare the efficiency among different actions with a particular state. So, by addressing this problem, the A2C algorithms produce a more stable model than the original one. And Bluetooth also takes advantage of transfer learning technique and considers hardware limitations. And therefore, it not only produces really efficient knob configurations, but also ensures the resource consumption. And we can see at the experiments here. The first one is to evaluate the transfer learning technique. It is apparent that applying the transfer learning technique, the red columns, the latency slightly improves compared to the cost only. Although employing transfer learning offers some benefits, but it requires more training time, as can be seen in the second figure. So it's up to the database administrator to decide whether the transfer learning technique is worth it or not. And the second experiment is the author used the same knobs as the previous one, but they added to another discrete knob called degree of parallelism. The feature of this knob is that it is not well reflected when we optimize the cost only. So here we can see the red column, or the transfer learning technique, improves pretty much compared to the cost only or the default settings. And as I mentioned earlier, it requires more training time. However, it is a good trade-off. So and here the result shows that the Bluetooth allocated memory used under the defined limits, which implies that it not only produces efficient knob configurations, but also strictly abides by the resource constraints. And this shows that Bluetooth is also scalable to the database size, and by increasing the size of the database by 10 times, the training time doesn't grow exponentially. And next, when compared with other existing tools, Bluetooth achieves more satisfactory performance. But it doesn't have some limitations. First, it fails to capture certain information, for example, the structure of table joins or the query execution plan, which is really useful for strengthening the RL agents. And second, it is unable to tune queries that execute simultaneously. But thankfully, the Google DeepMind devised another algorithm called asynchronous advantage actor critic, which can accelerate the training process by supporting several agents concurrently. So the next system I will introduce is a CDB tool. This system is mostly used on the cloud database. So here, the users will send a turn request to the interface, and then it will be sent to the controller. Or the database administrators themselves can send training requests directly to the controller. And from here, the requests can be conduct stress testing on the cloud database, or it can be then replayed by the workload generator, and then these workloads be sent to the metrics collector, and the process data will then be retained in the memory pool, or it will be sent to the RL agent to produce the new knob configurations, and this will be delivered to the recommender and then subsequently deployed on the cloud database. So having a deeper look in our agent, we can see that the CDB tool is primarily made of deep neural network, which receives database current states as inputs and produces recommended actions as outputs. These recommended knobs will subsequently be deployed on the cloud database to execute the current query workloads. And the cloud database will return the current state in the metrics, and these metrics are then fed into the agent to generate another knob recommendations, and this process will repeat until conversions. So having a look at the algorithm here, the deep deterministic policy gradient applied in the CDB tool. Like most other policy gradients, it has a parameterized functions actor and a critic functions. The critic will guide and direct the learning process of the actor by evaluating the knob settings produced by the actor concerning the current cloud database instance. It offers certain benefits. First, it requires diversity rather than an extensive amount of data. It can recommend high-dimensional continuous knob configurations. It can propose an end-to-end approach, which helps to mitigate errors, improve the accuracy of knob settings, and consider important degree of different knobs. And it is well adaptable to multiple workloads and hardware settings in cloud environments. So, having a look at the experiment, we all know that the RL agents need to obtain initial knowledge by using training steps and training samples. So here, the CDB tool uses a comparatively small number of steps, but its performance is pretty high compared to existing tools in this figure. Next, Here in this experiment, when the number of knobs need to be tooled increase, the CDB tools still maintain its performance. So this shows that the CDB tools is pretty good at handle the high-dimensional continuous knob space. Next, it is adaptable to workload change, memory size, and disk capacity, but it does have some limitations. First, it cannot provide up-to-date recommended knob configurations for incoming workloads, leading to poor performance. It requires multiple executions of SQL workloads, resulting in time-consuming. It only provides coarse-grained tuning and cannot perform fine-grained tuning, which makes the system unadaptable to diverse workloads. To conclude, RAO-based methods mitigate the data collections problems. They can adapt to dynamically ever-changing environment. Bluetooth and CDB tools offers different benefits for database knobs tuning problems, and these two systems emphasize the capability of RL agents when optimizing the performance with limited training samples and complex database. And database tuning is a reactive task, meaning that it will only be addressed when needed. And besides, this report also acknowledged the existence of diverse array of tuning tools with various benefits using for different types of database and query workloads. Indeed, no one solution fits all. Therefore, I suggest developing a novel system that can identify which tools to generate the best outcomes at each stage. Moreover, it must be compatible and scalable for other tools to utilize the process data at previous stages. So that's all what I want to say. Thank you for your listening.